So for problem 26, we want to eliminate the parameter to obtain an equation in x and y. So we're given these two equations here. X is equal to e to the 2t, and y is equal to e to the t plus 1. And we want to eliminate the parameter t to just get x and y. Well, there are several ways to do this. Like you can take the ln of both sides for the first equation, but I'm not going to isolate t at first. What I want to do is isolate e to the power of t is equal to something in terms of x, because if I do this, then I can plug it into the y equation. So I'm going to take x, actually before I do this, I'm just going to say we have that e to the 2t, well that's just e to the power of t squared, right? Because when you raise to an exponent, you just multiply it. So we have that x is going to be e to the t squared. And so I'm just going to take the square roots of both sides. So I have that square root of x is equal to e to the t. So once I have this, I can now plug the expression of e to the t back here. So I'm going to do that. Y is equal to e to the t, but as we saw, e to the t is square root of x, so square root of x plus 1. And this over here is our parametric equation that we have eliminated the parameter t. However, we are not done yet because the parameter t has restrictions. It goes from 0 to 25. So we do have to put this restriction here, because if we don't, we're just saying that the curve goes on infinitely, which is not true. So what we're going to do here is we're going to take the x equation, because now we're treating x as an input, and we're going to see how x is bounded given the boundaries of t. So let me remove this here. So I'm going to plug in the first boundary, which is t is equal to 0. So when t is equal to 0, so that's one of the boundaries, x is going to be equal to e to the power of 2 times 0, so 0, and e to the power of 0 is equal to 1. So that's the lower boundary. And the upper boundary, 25, so when t is equal to 25, we have that x is going to be e to the power of 2t, so to the power of 2 times 25, which is 50. So we can see here that x is going to be bounded between e to the 50, which is the upper boundary, and 1, which is the lower boundary here. Let me see if I've missed anything. No, I have not. So from here, what we're going to do is now we're going to describe this curve and indicate the positive orientation. So this curve here is just the square root function that has been shifted upwards. So it is the curve is a square root function shifted 1 unit up. 1 unit up because of this plus 1. And now we just have to indicate the positive orientation. So we have to show where it begins and where it ends. So it begins at, so we can see that the lower boundary for x is 1. So it begins at x is equal to 1. So 1. And now what I'm going to do is just plug in 1 here to get the value of y. So f of 1. So if x is equal to 1, that means y is going to be equal to the square root of 1 plus 1. So y is equal to 2 in this situation. So it begins at 1, 2. And let me erase all of this. And now we're going to test the upper boundary. So the upper boundary is, the upper boundary for x is e to the 50, right? Because we begin at x is equal to 1 and end at x is equal to e to the 50. So, and ends at e to the 50, comma. If we plug in e to the 50 in this equation that relates to x and y is going to be square root of e to the 50 plus 1, which is the same thing as e to the 25 plus 1 if we take the square root of e to the 50. So e to the 50 is the x value for the boundary, and e to the 25 plus 1 is the y value. So that is it. This is the curve that we have, and the boundary goes from x is 1 to e to the 50, And we put here the y coordinates as well, just so that we can see exactly where the point begins and where the point ends.